this is section 7.4, and the title of the section is Lengths of Plane Curves, but really this is a section on arc length and surface area. So if a curve happens to be a polygon, then the arc length is the same as the perimeter. Now it's kind of weird because a polygon is a simple closed curve made up completely of line segments. We don't think of a curve as being line segments. We usually think of a curve in normal everyday language as being, well, curvy, kind of wavy and stuff. But a straight line is a form of a curve. All right? So in this case, if that curve is a polygon, then the arc length is the same as the perimeter. If the curve is not a polygon, then we're going to follow our usual plan of breaking the curve into smaller measurable parts and finding the length. Now here's our arc length formula. This is the one on your formula sheet. Let's look at where it comes from. I'm going to derive this formula for you. You do not have to know how to derive this formula. I know some of them I did ask you in the past, to derive for me, like, the derivative of e to the x. This is not one. I just want to show you where this formula comes from. So let's suppose that a curve C is defined by the equation y equals f of x, where f is continuous on this interval. We can get a polygonal approximation for the length of the full arc length of the curve by dividing this interval into n subintervals with these endpoints. And let's go ahead and do it so that these subintervals all have equal width. And that equal width we're going to call delta x, that little distance there of x. I think you can probably see where this is going, right? That little delta x is what's going to turn into our dx here. And then this integral is going to be the sum of all of those little small measurable pieces. So looking at just some generic curve, will curve here of y equals f of x. If I have that interval from a to b subdivided into equal parts here, each one having a distance of delta x. Now if I take the limit as n goes to infinity, this approximation becomes more accurate, because I'm going to get more and more of these intervals, and these intervals are going to get infinitely smaller. So what I'm going to do is take the length of the line segments in those intervals, and then these line segments, you can see right here, that line segment is, it's a good approximation, but it's not exact. There comes a point where if you just think about this as a curve on your calculator, when you zoom in, zoom in, zoom in, zoom in, there comes a point where this curve starts to look like just a bunch of little tiny straight lines. And that's what we're going to take advantage of. We're going to take this limit as n goes to infinity and find this, almost infinite number of points, and find the straight line distance between 2 points, boop, 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 over and over again, all throughout that interval. So the arc length formula becomes the limit as n goes to infinity of the sum as I goes from 1 to n, I being these little, x of i's, of piece of I minus 1, piece of I, and this absolute value looking notation is a way of saying the length of the curve between two consecutive points. So that's what that notation says, that this is just saying, hey, the length between these 2 points, and they are consecutive points. Now the length between any 2 consecutive points, we're just going to use the distance formula for that. If you want to know the distance between 2 points, we're just going to use the distance formula. Now you might remember that from algebra, you might not, but that's the distance formula. The distance between any 2 consecutive x pieces right here is always constant. That was that delta x, so I don't need those i's there. I can just say, hey, that's just delta x. Here, the distance between any 2 y's, that's going to differ because, my function's kind of going up and it's coming down, so those y distances are going to be different. So I'm going to leave that I in there, indicating that there is going to be some kind of variation. So you can kind of see this, this distance formula, which is, of course, derived from the Pythagorean theorem, is going to simplify to just look like this. And then here's where it gets really clever. You have to apply the mean value theorem from Calc 1. Now the mean value theorem says that the derivative, or the instantaneous rate of change, is the same as the average rate of change on an interval. So it says that, hey, if you are on an interstate for an hour and your average speed was 80 miles per hour, at some instant in that time frame, on that distance, at some instant your speed had to have been 80 miles per hour. Right? That's what the mean value theorem tells us. So algebraically, the mean value theorem says that this average value is equal to that instantaneous value, or that average rate of change is the instantaneous rate of change. Of course, the instantaneous rate of change being our derivative, and this average value being our slope, So kind of changing, so all I did was multiply both sides by this denominator here to get rid of the fraction. This was the same as delta x, this was the same as delta y sub I. So originally we had that the distance between consecutive points was this formula. Now if I replace delta y sub I with this f prime, delta x business, I get this. I can factor out a delta x squared, because there's one right here, and there's a delta x squared right here. Because if I square all of this, I'm going to get the f prime squared and the delta x squared. So if I take out that delta x squared, that's going to leave me with 1 plus f prime of x sub k squared. All right, now, because this is multiplication right here, I can take the square root of this stuff and then the square root of this stuff and just multiply it. So the square root of a product is the product of the square roots. That turns into just a delta x by itself, because the square root of a squared undo each other. And then we have this. So this means that this limit that I started with becomes the limit as n goes to infinity of this sum of all of these things, because I just rewrote this distance between consecutive points in this form. And all of this, as n goes to infinity, is the same as that definite integral in that interval from a to b of 1 plus f prime of x squared dx. Alright, so I'm not going to ask you to ever derive that for me. I just wanted you to see where that formula comes from that's on your formula sheet. Alright, so let's use it. Let's find the length of the curve, y equals 1/3 times the quantity x squared plus 2 all to the 3 halves from 0 to 3. Alright, so in order to use this formula, you notice that we need the derivative. So that's the first thing I'm going to find. So I'm going to find the derivative of this. This is just a constant multiple. The derivative of this using the chain rule is going to be that 3 halves times x squared plus 2 to the 1/2 power, because I just subtracted 1 from the exponent, and then times the derivative of x squared plus 2. And then I just started cleaning stuff up. Those 3's cancel, those 2's cancel. So I get that this derivative is going to be this x times this stuff to the 1/2 power. So now I have to find the arc length. So here's my arc length formula. That's going to be the integral from 0 to 3 of the big fat daddy square root of 1 plus the derivative squared. So here's the derivative I just found. Now remember, you can use your calculator on these. I do want to go ahead and just kind of point out that this is the same thing as this. Okay, that 1/2 power is the same thing as that square root. So it might be a little easier when you go to put this in your calculator to put it in as that, but you certainly could just use that. I just decided, hey, you know what, I'm going to clean that up a little bit before I go and grab my calculator. Alright, so using the calculator, we get that that arc length there is 12. So this is going to be the square root of 1 plus x squared times the quantity x squared plus 7 is going to find that integral for me. And this is going from 0, my lower limit, to 3, my upper limit. And so there's my definite integral value of 12. Okay. So what's going to get messy about these is going to be, of course, the functions, and some weird points that we might run into, like what happens if the function's not, the derivative doesn't exist on the interval, or things like that. All right, so let's find the arc length of the graph of the natural log of the cosine of x from 0 to pi over 4. So there's the formula I'm going to use. All right, there's my function. So the first thing I'm going to do is I'm going to find the derivative. So this is going to go back to chapter 5. So the derivative of the natural log is 1 over u, and then this is the derivative of u, using the chain rule. And then I just clean this up. The sine over cosine is the same thing as tangent. So, and then of course that negative is just along for the ride. All right, so using my arc length formula, I get this, which I cleaned up a little bit. I went ahead and just said, hey, that negative squared is going to be the same thing as just squared. You can put that in your calculator, or if you notice that 1 plus tangent squared is the same as a secant squared, that's a Pythagorean identity from trig. If you notice that, and you're like, oh, hey, I'm going to go ahead and do that so that I just have to integrate secant, you can. Basically, any of these you can put in your calculator. So whichever one you get to, that's what you're going to do. And so my answer is going to be 0.881, but let's go ahead and see. So I'll tell you what, I'm going to go with this one because that's the one I feel like you guys would stop with. Whoops. Y equals the square root of 1 plus tangent x. I want to make sure that it squares. I'm not confident that if I put a squared right there that it's going to square that tangent. Let's see. Let's just see if it does. And I'm doing this. Do this in radian mode here. Yeah, you know what? I feel like that's going to be. I feel like putting this squared right here is going to square that x instead of that tangent. So let me show you how I really want to do this. So 1 plus parentheses tangent x squared, and then we'll close. So all I did was put parentheses around that tangent x and then that squared. That way it tells the calculator, hey, the tangent x is all squared. Because I think the way that I did have it, it was squaring that x. I'm not sure, but I just want to make absolutely sure, because sometimes the calculator does things. So let's go back to 7. Oh, see, that looks way better. It was a straight line before. I wasn't getting a good feeling from it. Now we're going from 0 to pi over 4. And so I get that 0.881. Now you'll notice that real quick, as soon as I put pi over 4 in, I realized, ooh, I need to be in radian mode. So before you start this problem, make sure you're in radian mode with this, because that pi over 4 is going to be in radians. Everything we do in calculus related to trig is going to be in radians. Okay. Now, in order for the arc length, in order to find this arc length, the derivative is going to need to exist for all of the values in that interval. Where would a derivative not exist? Well, from Calc 1, remember that there's 3 ways that a derivative may not exist. You may have a sharp point, you may have this cusp, or you may have a vertical tangent. Now what we can do to kind of bypass that is you can try rewriting the function as x is a function of y, and then see if dx dy exists for all y in the interval. You know, so it's like, oh, okay, well, if there's a vertical tangent here and I rewrite this, then it would just be a horizontal tangent, which is perfectly fine. So. All right, so let's see an example of when that happens. It keeps falling down. Looking weird. All right, so let's find the length of the curve of y equals x over 2 to the 2/3 from 0 to 2. There's the formula I'm going to use. So you guys know what I'm going to do first. I'm going to find the derivative first. Okay, so we get, there's my function. There's the derivative. So that's going to be that power rule and the chain rule. So 2/3 x over 2, you subtract 1, you're going to get that negative 1/3. And then the derivative of x over 2, which is 1/2. Because, you know, x over 2 is the same as 1/2 x. All right, so cleaning that up a little bit here, I can cancel those 2's, and I get 1/3 x over 2 to the negative 1/3. Just kind of cleaning that up a little bit for you and trying to get rid of that negative exponent. I flipped that fraction so that that would be a positive exponent. And of course, a 1/3 power is a cube root, so that's a cube root of 2, and then 3 cube root of x. Now, it's easier to see in this form where this derivative, because that's what this is, it's a derivative, where does that derivative not exist? So the interval that we want to find the arc length on is from 0 to 2, but this derivative function right here does not exist at 0. And if I put in 0, that's not good. The previous examples I did were all fine. We didn't have to even think about that. But I want to show you what happens when this happens. So, let's see why. If I graph the original function here, that's what it looks like. And from 0 to 2, there's the piece right there. It looks perfectly fine, right? You're like, yeah, I can find the arc length of that. What's the problem? The problem is there's a cusp at 0. And we know that differentiability is what's called a smoothness condition. So a function being differentiable everywhere on its domain means that the function is smooth. And this function is pretty much smooth, except right here it's kind of pointy. And differentiability does not like pointy. So that explains why that doesn't exist. All right, so let's rewrite that original function as x is a function of y. It's right now as y is a function of x. So basically, let's take this and solve it for x. All right, well, if we got to solve this for x, we need to undo this 2/3 power. The inverse of a 2/3 power is a 3/2 power. So I'm going to need to 3/2 power both sides of that equation. Because remember, if you have a power raised to a power, you multiply the exponent. So if I multiply 2/3 times 3/2, it just becomes 1. Okay. So that will give me that y to the 3/2 equals x. Here. Right, so we get that y to the 3/2. And we get this x over 2 on the other side here. Now to get rid of this 2, I'm going to multiply both sides by 2. So that gives me 2y to the 3/2 equals x. Now, there it is. X is a function of y. Now, let's find the arc length of this from 0 to 1. Where did I get 0 to 1? Where did that come from? Well, I'm glad you asked. This 0 to 2 was my original x interval. Well, when x is equal to 0, y, here's my original function, right? I just plugged in 0 for x, and I got 0 for y. So when x is equal to 0, y is equal to 0. When x is equal to 2, there's my endpoint, the other endpoint of the interval. Plugging that into the original function here, I get 1. So there's my interval for the y values. So basically I did all that stuff and now I have to start all over. All right, so now we're just starting all over. Now I've got this function from here to here. All right, so you know what I need to do. If I'm going to find the arc length, I got to find the derivative first. So let's find the derivative of this. So there's my constant multiple of 2. The derivative of y to the 3/2, just a power rule. Those 2's will cancel, and I get 3 square root of y, or y to the 1/2, whichever way you want to write it. And fortunately, this function exists everywhere in that interval. The square root of 0, fine. Square root of 1, fine. Everything in between, fine. So my arc length, plugging that stuff in for the arc length, I get this, which I just cleaned up a little bit because that's going to be 9y. And then again, we're just going to use the calculator. That's going to be the square root of 1 plus, there's not a y on my calculator. If you have a calculator that has a y, feel free to use that y value, but since I don't have a y, I'm just going to use just a generic x there. And that's going from 0 to 1, so I get that about 2.27 business. All right, last part of this section. In sections 7.2 and 7.3, we revolved a region around an axis, just some kind of horizontal or vertical line, and we formed a solid of revolution, right? We can also revolve a curve around a horizontal vertical line and form a surface of revolution. Instead of forming an entire solid, so what we did was in 7.2 and 7.3, we took a curve and we said, hey, here's this entire region. And so when I take that region and revolve it, I made a three-dimensional object. I guess I'm still making a three-dimensional object. I made a solid. Right? If I just revolve the curve and not an entire region, I'm going to get a solid as well, but it's going to be hollow inside. So we can just talk about the surface of this thing without talking about the volume or what's inside of it. We're going to talk about what's on the outside. So if we talk about revolving a curve around a horizontal or vertical line, we're going to form what's called a surface of revolution. The derivation for this surface area formula is in your book. It's not pretty. I love to derive formulas for you and show you where they come from, but it's not pretty. Of course, it uses the arc length formula, so there's that, but it really comes from using a whole bunch of little cones, little frustums, and adding up all those little tiny baby surface areas, and so that's where it comes from. But anyway, so here's my surface area. The r of x is the radius as a function of x. That's not r times x. Right? That's just the radius as a function of x. This, of course, is the arc length, and the surface area is formed by summing all the surface areas of those little frustums. Now, a frustum is just a truncated cone, so it's just a cone with the top lopped off, the pointy part lopped off. All right, so let me just show you how to use this surface area formula, and this is the last example for this section. So let's find the area of the surface formed by revolving this graph on this interval about the x-axis. So here's what it's going to look like. We get that 2 square root of x from 4 to 9. And we're going to revolve it around this axis. So it's going to be this kind of shape. I didn't really do it justice. It's going to get a little smaller. Just like something like that. This is why I use, that website in class instead of drawing it myself, because I'm not a good artist. The R value, just like it was in 7.2 and 7.3, we know how to find these R values. And this r is following this function right here. So we know that this r value is a function of x. It's just going to be this 2 root x. Now, using this surface area formula, we get this r of x, and then we have this arc length. Now remember, for arc length, we need the derivative. So I went ahead and wrote the formula out, but then I needed that derivative right there. So I kind of came down here and started working on the derivative of 2 square root of x. All right, so 2 square root of x is 2x to the 1/2. The derivative, of course, is going to be that constant multiple of 2, and then the power rule, 1/2 x to the negative 1/2. Those 2's cancel, and I get x to the negative 1/2. So that's where that came from. All right, if you just want to clean that up a little bit before we put it in the calculator, this is going to be the square root of 1 plus x to the negative 1/2 squared. Now, just in case you're wondering where this 1 over x came from, x to the negative 1/2 is 1 over the square root of x. If I square that, I square 1, I get 1. I square the square root of x, I get x. All right, so that's where that came from. You could also multiply those exponents and say, oh, well, 2 times 1/2 is negative 1, and x to the negative 1 power is, boop, 1 over x. Same thing. So, all right, let's put this in the calculator. And call it a section. So we're going to have that 2 pi times 2 square root of x times square root of 1 plus 1 over x. And that's going to be from 4 to 9. Okay, so we get about 171.26 in there. Okie dokie, so that is going to finish up section 7.4 for us.